Okay, so then we can start things.
Okay.
Mm-hmm.
Yeah. Can you see my writing?
Yeah.
Okay, great. Yeah. Right. Okay. Yeah. Sure. So you tell me when do I need to start?
Yeah. Okay. You can actually start now.
Okay.
So,
Okay. Great.
Xu.
Okay. Thank you. Yeah. Right. Thanks for the invitation. You know, it's my great pleasure to give a talk in such a nice conference. And all right. Since the camera on my iPad is not very good position, I gonna if it's okay, I gonna turn off the video and just share my note with you. Right. Mm-hmm. Okay, great. So my talk today is sort of give a realization of Gelfand-Tsetlin systems using the so-called WKB analysis. So Tsetlin systems. As we have seen from Anton and Jeremy's talks, we know that Gelfand-Tsetlin have different, origins. I guess in their talks, they showed that how to derive Gelfand-Tsetlin system from some tropicalization of Poisson brackets or Poisson geometry. And during this talk, I'm gonna give a realization of Gelfand-Tsetlin system from complex analysis, the so-called WKB approximation. So the tool I'm gonna use is a so-called WKB, or as well as the so-called Stokes phenomenon. So if you go to the Wikipedia web page, it will tell you that Stokes phenomenon means that in complex analysis, a function on complex plane can have different asymptotics at the singularities as your parameter z goes to the singularity from different directions. So this is a so-called Stokes phenomenon. So many classical functions have such a phenomenon. Let's take two examples. So the first part of my talk, like the first 40 minutes, includes an introduction to the Stokes phenomenon of differential equations. So I'm not assuming everyone knows this is familiar with Stokes phenomenon. So I'm gonna give a lot of background introduction. So let's look at the function exponential 1 over z. So we know that this is an entire function, except that at z equals to 0, it has an essential pole. And if we look at what happens near this essential pole, for example, if we let z, the parameter z, goes to 0 from the left half plane, this function is exponentially decay. But somehow, if we let the parameter goes to 0 from the right half plane, so it becomes an exponential growth function. Therefore, it has different asymptotics as z approaches to 0 from different half planes, and the asymptotic behavior changes as you cross the purely imaginary lines. So this is one example of Stokes phenomenon for exponential function. Let's look at another example. Let's take a more complicated. Right. So let's take the so-called Chroma function, or also known as the confluent hypergeometric function. So this is a function with parameter z, with another extra 2 parameter a and b. It's defined by a Paul series, taking the form that an over bn times z power of minus n divided by n factorial, where n taking the summation from 0 to infinity. And this function, here I should tell you that an by convention is a product of a plus 1 up to a plus n minus 1. Yeah, the similar for bn. Right, so this is also an interior function, except that at z equals to 0, it has an essential singularity. All right. So we can think of this as a sort of twist of the exponential function in the previous example. And by the known asymptotics of Chroma function as z go to 0, so the asymptotics of Chroma function near 0 has this expression. Here is gamma is simply the Euler's gamma function. So as z goes to 0, with some chosen branch of log z, since here we take this z power of a. All right. So if we look at this expression, we found out that, just as before, at z equal to 0, this function has a singularity. And if we let z approach to 0 from the left half plane, then the first term is exponentially grows. So the first term dominates. Well, if we let z go to 0 from the right half plane, then the first term is exponentially decay, while the second guy is a polynomial growth. Then the second guy dominates. So the second term win on the right half plane. So it shows that it shows that the Chroma function has different asymptotics as z go to 0 from left or from right half planes. And the asymptotics behavior changes. The asymptotics jumps as you cross is purely imaginary rows, lines, purely imaginary axis. So the asymptotics, just as the exponential function, asymptotics jumps at is purely imaginary rows. Okay. So these are two examples of Stokes phenomenon. Yeah. Any questions on these two functions? So, okay, if there is no question, so let's give a remark that these two functions are actually solutions of differential equations. Okay. Yeah. And in general, if we take certain differential equations whose coefficients have poles, then the solutions of the differential equations will have Stokes phenomenon. Yeah, just like these two examples. So in my talk, I'm gonna consider the following linear system of ODEs. So this is a system. And consider the Stokes phenomenon of its solutions. So the ODE I'm gonna taking is this form. Where the functions is now valued inside invertible n by n matrix. Let's take the type A case. Well, the coefficients U, well, this U, like in our coefficient, is an n by n matrix with eigenvalues U1 to UN. And A is an arbitrary n by n matrix. Yeah. Okay. So if we look at this such a linear system, we found out that its coefficient has a second order pole at z equal to 0. Therefore, in general, any of its solution will have an essential singularity at 0. Right. Then right. This is a linear system I'm gonna consider. So in the following, let me give an introduction to the Stokes phenomenon of this OD or their solutions. So first, how to solve this linear system. So we can solve this system using the formal Power series method. So the first thing we're gonna note is that if we write a formal solution for this ODE, which takes this form, so here this is simply a Power series of matrix valued functions. Each HK is a constant matrix times the singular part exponential minus U over epsilon Z. Sorry that here I forgot to say that epsilon is a real parameter. It's a non-zero real parameter. So this is gonna be the WKB parameter in the end. And then times Z power of bracket A over epsilon. So here, the bracket A takes the diagonal part of the residue matrix A. So this is a diagonal part. Of A, right. So basically, we take such a formal solution. So it says that the formal Power series, if we call, let us call the formal Power series by H hat Z, then so since bracket A takes the diagonal part of A and the matrix U is diagonal, then this formal solution says that this H hat is a formal gauge transformation to diagonalize our system. Then if we plug in, if we solve this system, if we plug in this formal expression to our system, we will get a recursive relation for the coefficients HKs. And the recursive relation looks like the following expression. So, right, minus HK times A over epsilon plus K times HK. Yeah. So on the left, we take the commutator between U and the HK plus 1. Right. And from this, so we can basically solve this recursion relation term by term, step by step, to get a uniquely solution. So this gives a unique formal Paul series. Yep. Right. And also from this expression, we find out that since on the right-hand side of this expression, we have k times, if we look at the last term, we have k times hk. So recall that each of these hk is a n by n matrix. And in the last term, we have k times hk. Therefore, we see that the matrix norm of each hk is more or less k factorial. Yeah. So it means that in general, the convergent radius of this formal sum is 0. Right. Yeah. So let me give a summary here. So in my talk, I'm gonna consider this linear system. So whose coefficients is given by U and A, where U is a diagonal matrix, and A is an arbitrary n by n matrix. So to find a solution, first I solve this system by a Paul series h hat z times the singular part. And then I see that the h hat z is uniquely determined by a recursion relation. But somehow if I estimate the norm of hk, I found out the norm of hk is like k factorial growth. Therefore, what I get is only a formal sum. It's in the convergent radius is in general 0. Right. So to construct a real solution, we have to resum such a formal solution using the so-called re-summation method. So there are many ways to resum a formal Paul series. Here, I'm gonna take the so-called Borel-Laplace transform method. Yeah. So to get from this formal solution to get holomorphic solution, I'm gonna use a so-called Borel-Laplace transform. Yeah. Yeah, I don't know if I should spend like a lot of time on these details. I don't know if people are familiar with this Borel-Laplace transform. Right. So let me give an introduction to that. So recall that h hat z, some basic idea in this Borel-Laplace transform. So this h hat z is simply a Paul series, and we can rewrite it as hk divided by k factorial, then times k factorial. But here I replace k factorial by gamma function. So basically, in this equality, I did nothing. And then I replace this gamma function by integral. What I get is an hk over k factorial times a power of k, and then the integration from 0 to infinity of t power of k exponential minus t and dt. All right. And then I formally shuffle taking summation and the integral. So this is where the Re-Summation procedure happens. So here I switch taking sum and the integral. What we get is an integration of the following function times e minus t hk dt. Right. And if I introduce a new parameter, let me call zt as t here, then we can rewrite this integral as 1 over z times another integral. So what do we get here? It's hk over k factorial t power of k times exponential minus t over z dt. Right. Right. So see here, I was starting from a formal Paul series, and somehow in the middle I formally switch summation and the integral. In the end, I get an integral expression. Right. Now, if I define a function gt by the integrand, we know that recall that the formal Paul series H hat. So if we look at the top of my note, recall that we have the norm of hk is like k factorial. Therefore, the function gt given by this Paul series is holomorphic in some small disk around t equals 0, right? So as long as we can, as long as this new function gt can be analytic continued to infinity along, from the small disk along some direction, and has a nice growth, which means if its growth is less than exponential, then, well, if this happens, then the right-hand side of this equality, recall that this guy is simply, so if we, right, this is a remark here. Sorry, I didn't arrange this note very well. So let me, as before, so we have, if we continue this identity, what we get here is integral for the function gt times exponential minus t over z, right? Yeah. Therefore, as long as we can take the analytical continuation of gt from the neighborhood of 0 to infinity along some direction, and as well as if gt has a nice growth, if its growth is less than exponential, then this is a holomorphic function. And this is actually a holomorphic function in some domain of z.
That's dt in the integral, by the way.
dt, right, of course, sorry, dt. This is a holomorphic in z in some domain. I'm gonna clarify later. Yeah. So this is a basic idea of Barreau-Laplace transform. It works for any formal Paul series of Riemann order 1, like in our case, which means the coefficients of the Paul series has k factorial growth, then we can use this method. Try to get a finite sum out of the formal sum. Yeah. Okay. So this page, I hope that this page already shows the basic idea, and it motivates us to define, right, from this remark, it motivates us to define the Borel-Laplace sum or Borel-Laplace transformation along a direction D, right? Yeah. So a Borel-Laplace transform of a formal Paul series along a direction D. So here D is a direction starting from 0 to infinity. If I draw a graph, so this is direction from 0 pointing to infinity. So it's a direction. So the Borel-Laplace transform of H hat is by definition the integral z/1 and the integral of from 0 to infinity along the direction D, and then hk over k factorial tk. So this was called gt before, right? And then times exponential minus t over z dt. Okay, very good. Yeah. So this is a definition of Borel-Laplace transform along a direction D for a formal Paul series. Any questions on this definition? Yeah. Okay. So recall that our goal is to define holomorphic, to find holomorphic solutions. Therefore, I should tell you when the remark in this box happens, right? And this is a classical theory. Maybe before Bockhoff in 1909. Which says that we can always, which says that if the direction D doesn't coincide with finite many directions, coincide with a finite many direction R times ui minus uj. Recall that u appearing in the coefficients of our ODs, right? And U is a diagonal matrix with eigenvalues U1 to UN. So basically here, we take the difference of UI and UJ, which is a complex number. We project this complex number to the complex plane. So we have UI minus UJ, or another UK minus UL, and so on. Then we draw a ray from 0 to infinity across UI minus UJ, and so on. Then we can cut the complex plane by finitely many directions. All these directions is determined by UI minus UJ. Well, if we take any direction D, which doesn't coincide with this finite many direction, then the Borel-Laplace transform of H hat is actually a holomorphic function. Matrix valued function, of course, is a holomorphic function in a sector region on S d minus 2 pi and then d plus 2 pi. So here this S d minus and d plus denotes a sector region near 0 with opening angle pi. Yeah. So basically this sector here, let me see. Okay, so this sector here is a sector centered at D with an opening pi. Yeah, right. Okay, so this theorem says that as long as the D doesn't coincide with this finitely many directions, then the borrow sum gives us, indeed gives us a holomorphic function, which is defined in some sectoral region. Yeah. Right. Any questions on this theorem? Okay. If there is no questions, let's carry on. So, all right. So here I give a simple remark. So recall that this, by definition, if we look at the first 2 pages, so by definition, this borrow Laplace transform can be seen as a map from the set of formal sums to the set of holomorphic functions in some domain. And this map is, of course, it's a linear map, and it's also compatible with differential operators, right? Then it means that the borrow Laplace transform of H hat satisfies, with respect to Z, satisfies the same differential equation as satisfy the same differential equations as H hat Z, satisfies as a formal Paul series. So given this remark, we can conclude that, so this is, I don't know who found this theorem first. Probably you could tell me, but at least it was known to Birkhoff, or even earlier, I don't know, 1909 or 07, 09 for differential equation, 07 for difference equation. So it says that on each sector, recall that we have finitely many directions which cut our complex plane, and we can take the sectors. Let me redraw this graph. So recall that the configuration of U, the diagonal matrix U, determines the ways how we cut the complex plane. And then we can label these sectors. For example, I can call this as sector 1 or 2 or I, and then I label the next one by I plus 1 and so on. So each of these sectors is bounded by 2 adjacent directions. And then on each of these sectors, let's call it sector I. For example, in this sector, there is actually, by the borrow Laplace transform, a holomorphic fundamental solutions of our linear systems. given by the Borel Laplace transform of H hat times a singular part. This is simply because the Laplace transform satisfies the same differential equations as H hat. Therefore, after the resummation, it's still a solution. Right. Yep. So where this D is any direction inside this sector. Yeah. For example, I can take any direction D inside this sector I, and then I take the Borel Laplace transform of H hat along this direction. What I get is a holomorphic function. And then after multiplying this function with a singular part, I get a holomorphic solution to the original linear system. Yeah. Right. So in this way, we construct in each sector region, we construct a holomorphic fundamental solution to our system, but only defined on some sectorial region. And furthermore, so the solution, each of these solution is canonical. It's unique, it's canonical. Each of is Fiz. So recall that this is a fundamental solution is actually a canonical solution. Let me explain what I mean by canonical. So here, this canonical means that each of this Hiz is the unique, therefore canonical. Is a unique solution with a prescript asymptotics with a prescript asymptotics that Fiz times exponential u over z times epsilon times. So basically, I move the singular part to the left, then this is going to be asymptotic to identity matrix as z go to infinity within a sector I. But actually, here I didn't give all details. It should be a super sector, a sector with an opening bigger than pi. But let me ignore some technical details. All right. So let me recall what we did in this page. So we take the Borel Laplace transform of H hat inside each sector to get a holomorphic solution in each sector. And these solutions are, each of these solutions is uniquely determined by the given asymptotics at the critical point z equal to 0. Therefore, they are canonical. Right. And this is actually, before that, is there any questions?
I'm a little bit, I'm just a little, isn't it the case that Z lies on the direction D? If you look at the definition, the definition of the change of variables, the gamma function is defined by integrating along the real axis, and then you rotate this real axis by multiplying T by Z. So I have the impression that D is determined by Z, whereas now you're saying that it's valid for all Z in the sector.
Yeah, here I didn't, because when I rewrite this gamma function, I can also add d here, right? So I can let everything write it depending on direction d. I didn't say that, right? Right. So this d is piece of the.
When you make the change of variables, t equals zt, then you're rotating anyway by multiplying by z. So
you're right. Therefore, I didn't write d here. So d, the direction d is a piece of the data in the definition of the Borel-Laplace sum. Right.
All right. Well. Yeah. Okay. Never mind.
Yeah, I gonna give a bunch of examples later on. I hope it will clarify. Yeah. Now I'm a little bit slow than I expect. But anyway, so let me recall what we did. So
you are very clear, which is very nice.
Okay, thank you. So at this moment, recall that. So we are studying a simple linear system with a pole of order 2 at z equal to 0. And then given an initial condition, which means given a prescribed asymptotics at z equals 0, we show that the solution exists. We prove the existence by Borel-Laplace transform, but non-uniqueness of the fundamental solutions. Non-uniqueness means that, so the solutions we constructed is associated with a sector. And for different sectors, the associated solutions may be different. This is what I mean by non-uniqueness. And this is actually the Stokes phenomenon, right? So recall that in the very first two examples, the gamma, the exponential and the Chroma functions, I said that Stokes phenomenon means that a function can have different asymptotics in different direction or in different sector regions. But somehow if I fixed in an equivalent way, I can say, if I fixed asymptotics at the critical, then I'm gonna have different holomorphic functions in different sectors. So therefore this is already, from this non-uniqueness, we already seen the Stokes phenomenon of these ODEs or of the solutions. So this is a Stokes phenomenon, right? And now, so it's equivalent to the previous definition. Okay, now let me introduce the so-called Stokes matrices, which is a measure of the Stokes phenomenon. So the measure of this Stokes phenomenon. So recall that before we have exponential Chroma function whose asymptotics jump along the purely imaginary axis. And a similar thing happens here. So recall that we have directions determined by ui minus uj and so on. And then we can take the canonical solutions inside each of these sectors. We want to measure the jump of this canonical solution. So what we do is simply we can take the analytical continuation of Fi from sector I in a positive sense to sector I+1. right? If we take the analytic continuation, then the ratio of these two solutions is an invertible constant matrix because they are solutions to a common ODE. Therefore, their ratio is constant. So this constant matrix somehow measure the jump or the change of the asymptotics as Z cross this ray. So let me introduce. So the so-called Stokes matrix is an n by n invertible matrix determined by as I said, the ratio of Fi and Fi plus 1 inside the defining domain of I plus 1. Yeah. So after Fi has been continued, analytic continued from sector I to sector I plus 1. Okay. Right. So this is somehow a little bit abstract, but now let me give you some examples for this Stokes matrix. By the way, do we have any break during the talk?
So it's just up to you. So if you want.
Yeah, I think you are the chair. So yeah. So it's up to you. So.
Okay, so then maybe.
No, maybe better not. How do you think?
Yeah, so better to go on, right?
Yeah.
Okay. Okay, great. Yeah. Okay. So as I said, the first part of my talk is sort of background, and my main goal is to derive the Gelfand-Tsetlin systems from Stokes phenomena or from the WKB analysis. And now, for that purpose, before giving some examples, let me focus on the real case, which means that most of the results hold for the complex case, but for the WKB thing, let me better fix on the real case. That is, from now on, the ODE, yeah, I'm gonna rewrite this ODE from time to time. The ODE I was thinking about gonna take this form. So where is iota is square root -1. So we'd better distinguish it from I. And U, let me assume U is a diagonal matrix with real entrance, with distinct real entrance, which means that each of these eigenvalues Ui are real and distinct. So we can think of this as a real part of the Cartan. And A, let me assume A is inside the UN, which is the n by n matrix, the space of n by n Hermitian matrices. Now so like in Anton and Jeremy's setting, yeah. Of course, we can still define the Stokes matrix. We can think of the Stokes matrix is basically assign a pair of these two matrices of one invertible n by n matrix. Yeah. So this procedure is very transcendental, like the following example, the 2x2 case. Yeah, let me give one example. So let's consider a 2x2 linear system which takes the following form. So this iota is square root -1. And let's take the residue matrix A as T1, T2, B1, and the B1 bar. So this bar is a complex conjugate times F. And as you may know, this second-order system can be reduced to a second-order differential equation whose solution is Chroma function. Therefore, one can easily write down one solution. And one solution for this one whole fundamental solution for this system takes the following form. So this is a 2x2 matrix. I only write down its two of its entries because it's a little too complicated. I just gave you some feeling how the solution looks like and how it helps us to compute the Stokes matrix lambda2 over epsilon and the power of lambda2 over epsilon and then f11. So recall that this is a Chroma function beta minus alpha plus 1 and then iota u2 minus iota u1 times z. So this is the first entry. And the entry in the second row, first column, takes a similar form. Okay, it's iota u2 over z epsilon u1 minus iota u2 over epsilon lambda2 over epsilon. And another Chroma function whose entry is given by minus alpha, beta minus alpha plus 1, and then iota u1 minus iota u2 z. And I will leave the second column. So here, I should tell you what are alpha, beta, and lambda1, lambda2. And actually, alpha is simply lambda1 minus t1, and beta is simply lambda2 minus t1. Well, this lambda1, lambda2 are eigenvalues of A, of the 2x2 matrix A. Okay, so therefore we can write down one explicit solution using the eigenvalues of matrix A. And then we can use the symptotics, using the symptotics. Recall that I showed in the very first page, the symptotics of Chroma functions, right, at the equal 0. Therefore, using the asymptotics of Chroma function, we can get this solution is actually asymptotic to f plus z times u plus, and fz is asymptotic to f minus z times u minus. So here, let me explain this f plus f minus right now, from left or from right. So here, recall, in our case, since u is purely, since our system has a purely imaginary diagonal part, therefore the cut are simply, the rays are simply the difference of all the ui, iota ui minus iota uj, right? Because any of ui, uj are real numbers. Therefore, the rays are simply purely imaginary axes. And then I will always denote the solution on the right sector by f plus and the solution on the left plane by f minus in any n by n case. In particular, in 2x2 case, this is a two solution. Right. So recall that f plus, f minus are determined by a given asymptotics. And therefore, using the asymptotics of Chroma function, we can easily compute the 2x2 connection matrix f u plus and u minus, which are given by gamma functions. Using this, we can compute by hand that the Stokes matrix in 2x2 case is simply u plus u minus inverse, which is in this case. Recall that asymptotics of Chroma function is gamma function, given by gamma functions. This is not surprised that in the expression of Stokes matrix gamma function appears. So everything here is quite explicit in 2x2 case. Okay, divided by gamma of 1 minus lambda 1 over epsilon plus T1 over epsilon times gamma function of 1 minus lambda 2 over epsilon plus T1 over epsilon. Okay, sorry, I don't know if you can see this. This is lambda 2 over epsilon plus T1 over epsilon 0. Yeah. So basically here I computed the Stokes matrix in an explicit way. So this is a 2x2 example. This example was at least due to Jimbo Miwa Yuno in 1978. Right. Any questions on this example?
Wait,
Right.
haven't you said before that the matrix is invertible?
Yeah, sorry, yeah. Thanks. Yeah, this is supposed to be exponential T2 over epsilon, of course. Sorry, yeah.
Mm-hmm.
You're right, yeah. Okay, this is
And there's
already
a question in the chat.
I'm not used to this note. Let me switch to the chat.
So the question is, so your F is not a canonical solution on this.
Oh,
Yeah,
yeah, I was wondering that, but I think I get it now. So F minus and F plus are the ones which are the canonical ones.
Yeah.
Okay, and
Yeah.
okay.
Yeah.
But
Because
you started with F because that's the one that's natural to obtain. Like okay.
Exactly. Because it's a very good question. Because the definition in the practice, we don't use the definition to compute things, right? The definition of F, the solutions with prescribed asymptotics involves like continuation of, if you still remember, the continuation of this guy from 0 to infinity, which is quite, which is not so manipulable.
Yeah, so that's not the good solution you will stumble upon when you
Therefore, I start from one solution and then compute its asymptotics at the same critical point, and then to determine the F plus F minus or the Stokes matrix.
Okay,
right. You're right. Yeah, and later on I'm gonna use So this is one example. Later I'm gonna show the n by n case. But this example itself is already very interesting. Why? We already see the Gelfand-Tsetlin system here, right? So let me tell you why. So the problem I'm gonna consider in this talk is to understand the analysis of geometry of Stokes matrix as epsilon go to 0. So the WKB. If time allowed, I'm gonna give you an introduction to WKB. But before that, let's simply think of this as a question that to understand the asymptotics of the Stokes matrix. In 2x2 case, of course, in the real case, we only have S plus and S minus, these two guys. And the asymptotics of these guys as epsilon, the real parameter goes to 0. Yeah. And this is simply a matrix. So let's denote its entry by ij and a. The problem is to prove that actually it has the following WKB type expansion, which is simply a exponential type expansion for generic U and A plus some lower terms of epsilon. Yeah. So there is some algebraic geometry framework, but my question here is to understand the asymptotics of each entry of Stokes matrix as epsilon go to 0. So this is not an easy question. For example, let's check the 2x2 case. So since the expression is quite, because that U is real diagonal, A is a 2x2 Hermitian in this case, right? So using the known property of gamma function, one can easily compute the asymptotics and show that the asymptotics is indeed given by the exponential type. Furthermore, we see that each leading entry of these things, here I only write down the leading entry. So this is given by exponential epsilon and the maximal of lambda1 and lambda2, which is actually lambda2. But let me write in this way. So in 2x2 case, if we compute for given U and A, if we compute the leading asymptotics of Stokes matrix, we will find that each leading asymptotics is given by the Gelfand-Tsetlin functions, action functions, right? Here, lambda1, lambda2 are eigenfunctions of A. So a remark is that, so we do see Gelfand-Tsetlin where I don't call it action variables. Action variables in this 2x2 case, right? So this is a toy example. Okay. Right. I hope this example is clear and it states our strategy and the problem. So in general, we want to study for n by n case the same question and want to see and want to find the leading term, the WKB approximation to give you the Gelfand-Tsetlin system, right? Okay. Is there any questions on this example? Okay, if there is no, let me switch to the n by n case. Yeah. Okay. Sorry. Okay, n by n case. So I'm gonna use the so-called the method, but I don't have time to give you the detail. But the method of isomonodromy deformation, it's meaningless because it's only a bunch of words. But if you know it, then method of isomonodromy deformation to prove the following theorem first. So the first theorem in this talk is as follows. So let me write down our equation again. So our equation is epsilon, a small real parameter, times dz equals iota u, a real diagonal matrix, plus a Hermitian matrix over 2 pi iota z times f. Yeah. And then the theorem says that for any fixed epsilon non-equals non-zero, the entrance of the Stokes matrix. In this case, we only have two sectors. Thus, two Stokes matrices are given by the following formula. So Fk, k plus 1. So the case row, case column, case row, k plus 1 column of the Stokes matrix takes the following form. So this AKK denotes the case diagonal element of matrix, the Hermitian matrix A, times the summation of I from 1 to k, and then the product of L from 1 to k of gamma function of 1 plus lambda KL minus lambda KI over 2 pi iota epsilon and times the product from 1 to K of gamma 1 plus lambda KL minus lambda KI over 2 pi iota epsilon divided by a similar expression, but involve lambda K plus 1 and lambda K minus 1, the eigenvalues of K plus 1 and K minus 1 sub-principal matrix of A. So I'm gonna explain my notation, and I guess Anton used or Jeremy used the same notation for this functions, for this eigenvalue functions, from 1 to K minus 1 of gamma 1 plus lambda K minus 1, L minus lambda Ki over 2 pi iota epsilon. Okay, this is the mean part. Furthermore, you should times exponential 2 pi iota phi Ki. So this is yeah, I don't have enough space, but this is inside this summation, right? And plus log of UK or UK plus 1 times lambda Ki over 2 pi epsilon, 2 pi iota epsilon. So this is actually a complex number of norm with norm 1. Yeah, right, plus lower order terms as U1 much less than U2, much less than U3, and so on. Let me explain. So here, the notation I used, like this lambda Ki, which is function of A, are eigenfunctions of A. So this is our eigenfunctions, like ordered eigenfunctions, eigenvalues of the upper left. I think Anton used to take the right bottom, right? Here I take upper left principal K by K submatrix of A. These are eigenvalues, which are real numbers for Hermitian case of A. Well, the phi Ki here are simply the corresponding Gelfand-Tsetlin or team angle variables. Angle variables. Okay. Yeah, let me explain this theorem. So first I have to say, at this moment, people has no clue how to write down Stokes entries of Stokes matrices, you know, in an explicit way. So I guess people conjectured for many years that the entry functions, right? The Stokes matrix can be seen, each entry can be seen as a functions of U and A. So certain functions are linear space, and the people conjecture that they are new transcendental functions. And the belief is maybe, you know, there is no explicit way to write down it. So what I did here is to compute the leading asymptotics of Stokes matrices as U1 much less than U2 and so on. So here this means I sent UN to infinity first and then UN minus 1 to infinity. So the lower order terms are in this sense, in this limiting sense, right? Yeah. And we already seen that the Gelfand-Tsetlin action and function action and angle variables already appears in this formula. Yeah. Any questions on this expression? So this is as U1 much less than U2 and so on. I compute the leading expression of Stokes matrix. But I will say later on, this is already a good model by some isommonodromy deformation property. This is a computable model for Stokes matrices for many purposes in integral systems or in representation theory. Right. So
sorry.
Yeah, sorry.
Fixed nuclei or the defined.
Hello.
So I wanted to ask: are these ongoing variables known explicitly in terms of maybe matrix element of A?
Yeah. Right. I don't know if it appears in Jeremy or Anton's talk, but the thing is that this is simply you take your matrix A, Hermitian matrix. There is a unique way. There is a systematic way to diagonalize its first K by K submatrix. So you can take a unique unitary matrix with a positive real along the last column. So this is inside UK, which is sitting inside UN as the left top corner and extending by ones along diagonals. Then you can diagonalize this guy to lambda K1 to lambda KK, and so this is diagonalized. Well, the K plus 1 column is denoted by that denoted the entrance in the K plus 1 entries by AK1, AK2 up to AKK. Okay, so this is a block matrix, of course. Yeah, and then each of this AK1 to AKK can be seen as a function of A, but they are not. But they are only defined on open dense subset, and then we can take phi Ki as an argument of AKI. Yeah, so this is a function on an open dense subset of the n by n Hermitian matrix. Yeah, so this open dense is cut out by the interlacing inequality, strict interlacing inequalities. Yeah. So in this way we can take the argument. Yeah. Okay. Yeah. Right. Now the thing is that I'm gonna give a remark on this formula, that if we look at this formula, we will find out. So this formula, the leading term of this formula is this gamma functions, and with the fast spin, right? With the fast spin so please allow me to erase this. I want to leave the formula in my note. So I need more space. So if we look at the expression, we found out that as U go to U infinity, here by U go to U infinity, I mean, I take this limit as people usually did in KZ equation, right? So, and then furthermore, as epsilon go to 0, we found out. So first, this is a expression. What I gave is the expression of the leading term of Stokes matrix at U infinity. Let's denote this limit by U infinity A in terms of Gelfand-Tsetlin variables, right? And furthermore, as epsilon go to 0, we see that these things are constant. The action are constant from this expression. Well, you do have some fast spin on this angle coordinates, on this corresponding Liouville tori. Yeah. So this corresponds to some correspondence between isomonodromy and isospectral deformation. Some widely believed correspondence between isomonodromy and isospectral. Some Re-Sum dynamics and so on. So, but I'm not going to talk about that. Let me go back to our original problem. Recall that our problem is to study the asymptotics of S plus UA as epsilon go to 0. Okay, and now let me give, based on this theorem, let me give another theorem. So actually, we did this for U near U infinity. So this is a joint work with Anton and Zhou Yan, postdoc in our institute. And later on, I'm going to say this is actually an analytic version of the tropicalization in Anton's and Jeremy's talk. This is actually geometrically, this is actually a tropicalization. So we see that for generic A, which basically means that if A lives inside the domain cut out by the strict Cauchy interlacing inequalities, we actually have the following thing. So this expression actually takes the leading asymptotics. So right, let me. By the way, should I define this coordinates on upper triangular matrices? This delta ij. I guess it was used in Anton and Jeremy's lecture, right? So if you forget, then Stokes matrix S plus can be arranged. It's actually an upper triangular matrix. And instead of entry coordinates, we take some cluster or minor coordinates on n by n matrix, upper triangular matrix. So we take for any I bigger than or equal to j, we take the column from I minus j plus 1 to j's column, and then we take the minor consisting of these columns and the first j rows. So this is then this delta ij in my notation is simply such a minor coordinates. Yeah. Right. So if we take the minor, so of course this minor is simply a polynomial of entrants. So if entry coordinates have exponential behavior, the minor of course do. So we take some polynomial combination of entrants, and then we let U go to U infinity in the previous sense. So basically here, what we get is the explicit expression in gamma functions, right? So this first limit is already computed by the leading term here. The norm, right? Because here I take the norm. If I take the norm of entrance, I will throw out all this fast spin. This is a fast spin. Right, as U go to infinity, each of this guy behaves not very good. But somehow if we take the norm, we can throw them away. And then we take epsilon go to 0. As epsilon go to 0, what we are left are some gamma functions if we look at the expression again, each term is gamma 1 plus some difference of eigenvalues over epsilon. So we know that the gamma function as epsilon go to 0 has a behavior that epsilon power of epsilon, right? It seems that they are not quite exponential type behavior. But the non-trivial thing is that they cancel out with these terms. It also happens in 2x2 case. I forgot to say that, to stress that on 2x2 example. But there is some non-trivial cancellation here. The leading term in gamma functions is not exponential, but they cancel out with some other terms. In the end, we do get this exponential leading term, and furthermore, we computed the leading term, which is simply given by the sum of Gelfand-Tsetlin action variables. So this is same type of formula in Jeremy and Anton's talk, J minus 1. Yeah. So this is a sum of the eigenvalues of I by I submatrix. I mean, this is not a, this is, as I said, this is a bunch of explicit computation, and also can be seen. Yeah, I'm gonna give a remark that how it's related to tropicalization of Poisson geometry. Okay. So basically in this theorem, what we proved. So the remark here is that what we proved is not for generic, right? Not for any U, but for the U in the infinity point. But for U to be, so this point has a name called the caterpillar point. So actually this n by n diagonal real matrices with distinct eigenvalues has a de Conteny process compactification. So if we think of, yeah, I don't know if I should say this, but geometrically, what we did. So if we consider this is marked each of these U1, U2, of course you can reorder them. So this is a configuration of H regular R, and it has a configuration by adding all these nodal curves. And if I send UN to infinity first, and then I send UN minus 1 to infinity and so on. So this, the corresponding real stable curve, rational stable curves, simply take this form, which looks like a caterpillar. So this is also called a caterpillar point by David. Yeah, Spear, right? David. Yeah, in her work. Yeah. Yeah, this is just a side remark. So basically, we didn't prove what we want for a generic U, but only for this limiting point. Yeah, at this moment. And now let me formulate. So I should stop at in 20 minutes, right? Okay, so in the following, let me first, I'm gonna do two things, formulate for a generic U case. Formulate analysis as well as a algebraic curve formulation for generic U case or conjecture. So this conjecture can be proved based on some estimate for Hamiltonian system, but I may not have time to say it. But then, mostly importantly, I want to give a feeling why this is true, why the Gelfand-Tsetlin system can be derived from this sort of asymptotics from 2 points of view. First, I want to take this tropicalization from the viewpoint of Anton Xiaomeng's talk. And then I want to give a feeling why it's true from the WKB approach, analysis. Yeah. Let me first do the second thing. Okay. So let me explain why we can derive Gelfand-Tsetlin systems from complex analysis. So first, from the Poisson geometric viewpoint, following the remarkable work of Philippe Boch, we already know that for any, okay, again, recall that our system is simply epsilon times df over dz equals iota u over z square plus a over 2 pi I iota z times f, where u is real and a is Hermitian. So for any fixed u, for any fixed u and fixed epsilon, the Riemann-Hilbert-Birkhoff map, or the so-called dual exponential map, is a Poisson map. So we take the dual of Lie algebra un, which is simply n by n Hermitian matrices equipped with the canonical linear Poisson structures. And it maps the dual Poisson Lie groups, which is, as in Anton's, which is rewritten as an. A is a real diagonal, n is a strict up triangular. So there's capital Un star. So this is a nonlinear Poisson structure from the dual Poisson structure, dual Poisson Lie group. So the map which sends any Hermitian matrix A to the Stokes matrix is a Poisson diffeomorphism. Yeah, this first appears in Philippe Boch's work, right? Yeah. See, this already, this setup. This is basically Anton and Xiaomeng's setup, right? They consider a family, a epsilon or T, or epsilon family of Ginzburg-Weinstein linear maps, and then take on one side they take the minor coordinates, and then they did this tropicalization, and prove that the tropicalization composed with limiting Ginzburg-Weinstein map defines the Gelfand-Tsetlin systems on UN. This is right. This is exactly the previous setup. So not quite right, because here we only proved the case U to be U infinity. For other U, you may already guess. For other U, we should expect what we get is a classical shift of argument, also known as Mischenko-Fomenko system. So this limit in their lectures are called the linear called the tropicalization of Ginzburg-Weinstein. This is, but at this point, this is tropical. Yep. So this goes back. So the Boch theorem established the correspondence between the tropical Poisson geometry and this WKB analysis. Okay, this is one way to think of. If you prefer the Poisson geometric setting, then this is one explanation. Okay, let me give you another explanation from the purely analysis thing. So analysis, WKB analysis. So let's see why we expect such thing happens. So again, let's take our favorite ODEs. And let's see what happens just by some. Let's see what happens. Let's check what happens as epsilon go to 0. Right. So in the last 10 minutes, I'm gonna. So first, let's assume, like in what people did. So this WKB stands for the names of 3 physicists. Sometimes it's also called WKBJ, or sometimes with Green or with Jeffrey's name. So there are some. So from 1926, when they study the Schrödinger equation. So you can think of epsilon is h bar in Schrödinger equation, and we try to solve this. We try to get a perturbative solution. So in our case, we assume we have a asymptotic solution, which takes this form. And we try to solve it in a, like in the form Paul series way, in this perturbative way. So that we have phi kz times epsilon power of k. And then plug in, comparing the leading coefficients, we simply get, comparing the leading coefficients, we get such an expression, which is nothing but the eigenvalue equations times phi z. Right? So if we rewrite, so this is simply the eigenvalue equation. Pi u to z. So why this is, it's a curve on, you can think of this as a curve on lambda z plane. Then one solution can be chosen as follows. So what we talked here are fundamental solutions. So all the omega z, phi z are exponential, are matrix value functions. So we can think of each of this omega z as a diagonal matrix is given by the integration of the eigenvalues. Then phi is simply the corresponding eigenvectors. And phi z, the column of phi z are corresponding eigenvalues. Eigenvectors. Yeah. Right. We can find asymptotic solutions in this way, in a formal sense. But now let's see what's the relation. So what I gonna show you is that the Stokes phenomenon in WKB is sort of algebraic thing on the corresponding spectral curve, the Stokes phenomenon in WKB. So recall that the Stokes phenomenon is a jump phenomenon of the asymptotics of solutions. Let's look at what are its behavior in WKB. So let's assume, so this is not rigorous, but let's just a feeling, let's assume the canonical solution. Recall that the canonical solution specified by asymptotics at z equals 0 has the WKB type behavior. Plus lower order terms, which are ignored here, and f minus, because that we have f plus, f minus, and assume they have such leading behaviors. Then just comparing the leading coefficients in the definition of Stokes matrix. What we get is, see, the Stokes matrix now depends on UA and epsilon, but independent of Z. If we take epsilon go to 0, what we get from this assumption or what we expect is simply Stokes matrix, or each entry of it is simply by comparing, some periods on your spectral curve. So this is independent of Z0. Yeah. Right. If you assume this canonical solution do have this WKB type expansion, we can expect this type of behavior for Stokes matrix. Right. And so this is simply some period. So here you can think of this as some integral, but actually in practice we can show this is actually period of the canonical one form on the corresponding spectral curves defined by the eigen equation, spectral curve, on the spectral curves. Okay, and furthermore, the last piece we need is how it's related to Gelfand-Tsetlin, right? Okay, if we look at the coefficients of the eigenvalue equation, so this is a period we're gonna compute over this curve. So see as U1 much less than U2 and so on. Computing the eigenvalues of this guy is exactly, if you compute the eigenvalues to be more precise, the periods over this spectrum are exactly the lambda KIs. This can be seen, right? For example, if UN is much bigger than left, the computing of the eigenvalue of this guy is simply computing the eigenvalues of sub n by n matrix n-1 by n-1 matrix of A. And this is exactly the degeneration. For those who know the shift of argument, the degeneration of classical shift of argument system or algebra to Gelfand-Tsetlin system as. So this shift of argument algebras are parameterized by U1 to UN. And in this limit, they degenerate to Gelfand-Tsetlin in some projective sense. And this is exactly, and what I said on the spectral curve is exactly some algebraic correspondence, some periods over spectral correspondence. Yeah. So this is from this WKB asymptotic solutions, as well as this degeneration of classical shift of argument to Gelfand-Tsetlin system, we should also expect the Stokes matrices has the Gelfand-Tsetlin system as a WKB approximation. This gives an explanation for our theorem. Right, I still have 5 minutes. 5 minutes, so right. So in the end, we make quantitative conjectures for general use case. Under the integrable systems, we should get is a shift of argument instead of the Gelfand-Tsetlin. And this also has a quantum version, which corresponds to eigenbasis beta vectors of quantum shift of argument subalgebras. Right, so for generic U and A. So actually, we can construct distinguished. So the only thing interesting here is we construct the distinguished cycles. Cij on the corresponding spectral curve defined by this equation on the lambda Z plan and then compactified in P1 on this spectral curve. We construct distinguished circles where this I is less than J and less than N. And then we conjecture that the WKB leading term of this minor coordinates of Stokes matrix at a generic UA, not just the caterpillar point, is actually the period of the canonical one form over these distinguished circles. Yeah, and there are some other, but time is up. So like all these integrals actually gives you the integrals of the shift of argument. These functions, they are functions for fixed U. They are functions on open dense subset of the space of A, and they generate the classical shift of it generates the classical shift of argument subalgebras. Also, we expect they satisfy the Rombas inequalities and so on. So this is, at this moment, this is a conjecture, and this conjecture should be proved by some widely believed correspondence between isomonodromy deformation to isospectral deformation in this setting. But this is, at this moment, this degeneration is sort of initial value dependence of a Hamiltonian system. It has not been, as far as I know, this is not being proved rigorous, but people has many formal arguments on it. Yeah, based on this type of technical issue, we can prove this conjecture. And I think my talk stops here. Thank you. Thanks a lot.
Thank you very much, Xiaomeng.
Thank you.
Are there any questions?
May I ask a question?
Yeah, of course. Please.
So I wanted to ask, what happens if we consider arbitrary complex matrices A and not just Xiaomeng ones?
Yeah, right. So the thing is that, okay, so the complex setting is very important since it's related to this Frobenius manifold thing, right? So this formula should work for generic complex A, and but I cannot prove it because in the method of isomonodromy here, to prove this theorem, I have to estimate the asymptotics of solutions of isomonodromy equations. For Hermitian case, the norm of solutions is constant. Therefore, it's automatically bounded. But for the complex case, I should estimate the solution of this PD isomonodromy equation and prove they have some behaviors like, I forgot. Yeah, I have to prove some estimate for the solutions of isomonodromy equations. Yeah, but that I cannot do. But somehow the computer program verifies it's indeed true. Yeah, because isomonodromy equation you should control its asymptotics. You should control the asymptotics of the solutions of isomonodromy deformation equation as you go to infinity. There is some estimate missing, but somehow the randomly chosen 4x4 matrix is, by computer programming is okay. But another very interesting question is that if you look at this formula, we already know that the Stokes matrix is, of course, Stokes matrix is holomorphic function on A. But the right-hand side, if we look at the gamma function, it's not quite, it's real analytic, but it's not quite complex analytic. It has some poles because gamma function has zeros if you consider the complex setting. And it may correspond to something that if you consider solutions of isomonodromy equation. And in the real case, the solutions are real analytic, but somehow in complex setting, they may have some movable pole, and this movable pole may concentrate to this limit, I guess. That I don't know, but what I can say is that the computer experiment suggesting that for complex A, this is still true for generic case. But somehow this formula tells you that it cannot be true for all the A because the right-hand side is not analytic. It has some poles, and it may, and it happens. It happens by some reason, yeah, like accumulation of the movable poles for isomonodromy equations. That I don't know, right?
Yeah.
Yeah.
So maybe it means that for some special ways, like for Jordan block, the asymptotic of the solution just changes.
Yes.
Yes. So, but I wanted to ask maybe even. Absolutely a stupid question. So, what happens with the number of parameters? Here you had this matrix S plus, and what else will we have in the complex case? Because it looks like
Right.
1/2 of parameters.
Right. Exactly. So in the real case, S plus equals S minus complex conjugate, but somehow in complexes they are independent, except along diagonal they coincide. And in that case, we also have a formula. So here I only write down Sk k plus 1, but for S like for S minus, we can have Sk k minus 1, given by a similar formula. Yeah.
Okay, thank you.
Yeah, and because this the entries of Stokes matrix satisfy the classical RLL formulation. Therefore, all the other entries are algebraic combination of the subdiagonals. Yeah. So therefore, therefore we only need to study the subdiagonals. The others are given explicitly by algebraic combination. So yeah. Thank you.
Thanks.
May I ask?
Of course.
So the formula for K plus 1 on the screen, reminds about the formula for matrix element of Chevalier generators of Gelfand in Gelfand-Tsetlin basis. Right, and is there any direct explanation of this fact?
Right. Yeah. So actually, I also compute a non-commutative case like the quantum. So I take a kz. So the quantization of this equation is a kz equation with two variables, and the Stokes matrix there satisfy the RLL relation, whose subdiagonals satisfy the, as you said, some quantum size relation for GON or SON. Yeah, and there, so basically there in the quantum setting, we also have a formula for the Stokes matrix, which is given in terms of Gelfand-Tsetlin basis. of UGON.
Mhm.
Yeah, taking the exact form. So each of this lambda then becomes the weight, of your representations. Yeah.
Right.
Yeah. So yeah. Yeah. So basically, yeah. So basically, in the quantum case, in the Q case, so you simply take this. KZ equation. Then you compute the Stokes matrix. You get the quantum Chevrolet generator, where so each of this F is valued in n by n matrix, but each entry is seen as the highest weight representation, and the T is just the Killing form. So this is n by n matrix. Each of these EIJ are generators of UGON, and through the representation is of course inside here, and H is the real value, and we study. So this T is fixed, and then so this Stokes matrix is now n by n matrix with each entry valued inside endomorphism U lambda. Sorry, each of here should be endomorphism U lambda. Yeah, and then the S plus satisfies the RLL relation. So this is exactly a quantum version of Borch's theorem. Recall that Borch proved that the classical Stokes matrix satisfies the classical RLL relation. So here, this R is a standard R matrix inside endomorphism Cn, tensor Cn. So here we use a tensor notation like 1, 2, 2, 3, and so on. This means subdiagonal entries of S plus are quantum Chevrolet generators, and as you go to caterpillar point, we also have explicit formula for this guy in terms of Gelfand-Tsetlin basis, and then as H go to minus infinity, that is as Q equals exponential 2H go to 0. So this is a WKB. We get, as what we did in the classical case, we get the Gelfand-Tsetlin basis, as well as the crystal operators acting on this basis. So because as Q goes to 0, this corresponds to crystal limit. So in principle, you should see this crystal operators in WKB. So this is exactly the quantum version of my talk. So these systems. Yeah. So you instead of the UA equation, you simply consider this KZ type equation and study its Stokes matrices. The important thing is that as you go to infinity at the caterpillar point, you have explicit formula for everything for the Stokes matrices. And since the U varies in an isomonodromic way, therefore the explicit formula at the caterpillar point is a model for for the application of Stokes matrices in symplectic geometry or like in this Gelfand-Tsetlin basis thing. Yeah.
Okay. Yeah, I see. Thank you.
Yeah, and in general, my guess was that for general U, this should give you the eigenbasis, right, of your shift of argument algebras, and it should give the cover you defined with Kamenitzer and Higgs and the other collaborator. So this.
So
this
you get
should,
some solutions of beta and Zas equations.
Exactly.
At such limits. I see.
Yeah. So basically, the space is the compactified H-react hat. What I computed is at the caterpillar point, the WKB approximation gives you this Gelfand-Tsetlin basis, and the crystal operators on it. And actually for any U, you should also, but there is some analysis issue, as I said here. You should also get this basis and the crystal operators. And then you should get a local system. So this is, I guess this is simply your cover with collaborators. And this, from analysis, this corresponds to the isospectral deformation, which explains your cover from representation theory, theoretic side here. Right.
Okay. Yeah, I see.
Yeah.
Yeah. Well, that's great.
Thank you.
Okay. Maybe other questions?
May I ask one more question?
Huh?
So I wanted to ask what happens with all the story in the special limit of this linear system, which can be solved in terms of hypergeometric function. I mean, hypergeometric function. I don't know, maybe like f n minus 1 n minus 1.
Yeah. Yeah, very good. So this is exactly the strategy I proved this theorem. So recall that this equation looks like this form, right? So you can consider it spectral curve, or otherwise you consider this linear ODE. And inside this limit, for example, if UN is much less than the left UIs, so this is basically degenerate to two systems. Because UN is much big, so you can prove in a regular sense this system decouple into two systems. One is this guy. So this is like the degeneration of shift of arguments to Gelfand-Tsetlin. And another one is n-1 by n-1 system. So you take the n-1 submatrix of these guys. So in each step, so if you let UN go to infinity, so this guy decouple to two systems. And this decouple, you should use solutions or asymptotics of solutions of isomonodromy equation to decouple the isomonodromy. So if you continue this way, in the end, you only need to study the Stokes matrices of this system, which is, as you said, the hypergeometric systems. So the solution of this system is, as you said, exactly given by the Chroma function of FNN. Yeah. This is one special case. Yeah. So actually, I used the asymptotics of isomonodromy to decouple this system in this limit, to decouple this system into a bunch of simpler systems, which where each of them can be solved by this confluent hypergeometric function. Yeah, this is one case. And another case is SU3 case, you can exactly compute anything using the Pauli V6. As far as I know, they are more or less Stokes matrices, you can compute it. Yeah. So this is a strategy.
I see. So I assume that all these gamma functions actually come from some connection formulas for
exactly. Exactly.
I see. Nice.
Yeah, because in this limit, you can decouple these systems, reduce these computations to these confluent hypergeometric functions, FNN. Right.
I see. Thank you very much.
Thank you.
Okay. So no questions, then thank you, Xiaomeng.
Thank you. Thanks again for the invitation. Okay.
Very much. So we we resume in 15 minutes. There will be the last talk on this conference by Boris Peking.